All right, so last time we said that we talked about propagation of errors. And that is determining the uncertainty in the result of a calculation if you're basing it on numbers that have uncertainties in them. So here's a question on what the calculated result should be from this, assuming all of these numbers have uncertainties in them. Okay. All right. Okay. Okay, so popular answer is C. All right, let's see. So let's do the multiplication first. This is 2 sig figs. That's 3 sig figs for 39.0. 0.0050 times 39. That's 0.195. And so this should only have 2 sig figs. Okay, but we keep that extra 5 just so we avoid a round of error, building up round of errors. And then you add that to 0.0072. So 0.0072. So if you do that, you're going to get 212, 2022. Okay? And if you did this, this is the last sig fig for this term right here, and this is the last sig fig for the first term. So the answer is 0.20. Okay? So here's 2 sig figs right here, because it's 2 sig figs times 3 sig figs. So this 1, 2. So that 9 right there is your last sig fig, even though you're keeping that extra 5 just so you don't build up round off errors. Okay, and now when you add the 2, you get 0.2022. And so since the 9 here is your last sig fig, this so the hundredths place would be the last sig fig. So the correct answer for this is A. Okay? All right? Okay. So let's move on. Let's talk about units now. The preferred system of units that's used in the sciences and for global trade is known as the SI system. SI stands for Système International, and it's basically a system that's evolved from what's known as the metric system. Okay, the worldwide authority on SI, that's the agency that is the authority on that, is the International Bureau of Weights and Measure. The acronym for that is BIPM. That's based on the French name. So that's, I think, Bureau International des Poids et Mesures. And so this website right here, www.bipm.fr, FR is France, /ENUS, that's English US, /welcome.html. If you go to that website, and that gives you a link to everything you need to know about the SI system of units. Okay, so let's just go over some of the important aspects of the SI system. The SI system defines what are known as fundamental quantities. And so it defines a unit for those 7 fundamental quantities. Okay. They were officially defined in 1960, and this is the link to that website that has the official definition. It tells you exactly what a kilogram is. The base unit for mass is kilogram. So the fundamental quantity is mass. The base unit is kilogram. Okay. So the SI system defines exactly what a kilogram of mass is. It also defines length. Okay, and so that's another fundamental quantity. And for that fundamental quantity, it defines a base unit as meters. So these are all official abbreviations for the units. kg is kilograms, m is for meters. S is the official abbreviation for seconds. It's not SEC. That's how you do it, I believe, in the metric system. It's just plain S in the SI system. Okay. The base unit for temperature is Kelvin. The base unit for amount of substance, which we're going to be dealing with a lot in chemistry, is the mole. A base unit for electric current is the ampere. And the base current for what's called luminous intensity, this is hardly something we'll hardly ever encounter in chemistry, is the candela, CD. Okay, so these are the 7 fundamental quantities in the SI system. So they define exactly what 1 meter is, exactly what 1 second is. Okay. Now, all other quantities that you can measure can be thought of as derived from measurements of fundamental quantities. So, for example, if you're interested in speed, well, to calculate the speed of something, okay, you divide the distance that it travels, so that's a length, that's a measurement of length, by the time that has elapsed. So we can say that speed is derived from measurements of length and time. So the derived unit for speed in SI would be the unit for length, which is meters, divided by seconds. So meters per second, okay, or you can use meters times second to the -1. So that's an example of a derived unit. Now, some derived units are given special names in the SI system. For example, the unit of energy, which is really a combination of kilograms times meters divided by seconds squared, okay, that is given a special name that's called a joule. And it has an official, all of these units in the SI system have an official abbreviation. So the official abbreviation for joule is capital J. Now, you may be wondering, why are there so many units that have been invented for measurements? Well, the reason is really convenience, and it took a while for people to agree on a standard also. And so convenience is the main reason, okay, one important reason, because people would prefer to use units that make so that the number that you write in front of the unit is easy to read or write. So for example, let's say you want to express the height of a person. Let's say you can say a person is 6 feet tall. Or would you prefer to say a person is 0.0011 miles? Obviously, feet is a more convenient unit for expressing the height of a person. So it's all about convenience to a large extent. Okay. The nice thing about the SI system of units is that these base units you have in SI, you can add what are known as prefixes in front of the unit to scale it down by powers of 10. So you can make a unit 10 times larger, or 100 times larger, or 1,000 times larger, or 10 times smaller, or 100 times smaller by simply putting a prefix in front of that unit. So that sort of allows you to write your measurements in terms of numbers that are easy to read or write. So let's illustrate that. Okay? The prefix n, lowercase n, that's officially defined in the SI system as nano, the abbreviation for the prefix nano, which means 10 to the negative 9. That means 1/1 billion. So if you imagine you have a meter stick, okay, you divide that into a billion parts. Each part, each segment would be 1 nanometer. Okay, that's a convenient unit to use when we're dealing with atoms in chemistry. If you have atoms in a molecule, you have a pair of atoms, a typical distance between them is around 0.15 nanometers. So you can see it's a very convenient unit to use for lengths at the when we're dealing with atoms, which is what we do in chemistry. Okay. All right, so here are some metric prefixes that you really should be memorizing. Okay, these are prefixes that I expect you to memorize. Giga is 10 to the negative 9. A good way to remember that prefix is you've probably seen the movie, what was that? Back to the Future. So 1.21 gigahertz, gigawatts of power. Okay, 10 to the 9 is a billion. Mega is a million. Okay. So official abbreviation for mega is capital M. Kilo is 1,000, so you should be familiar with that already. Kilometer is 1,000 meters. Kilogram, by the way, kilogram is the exception among the base units. It's already got a prefix in it. Gram is not the base unit in SI. It's actually the kilogram because that's the unit that they could actually define more precisely than the gram. So the base unit for mass in SI is kilogram. It has a prefix, okay? So, but when you add prefixes to mass units in SI, you add the prefix to grams. Deci is 1/10, that's 10 to the negative 1. Centi is 10 to the negative 2. So 1 centimeter is 10 to the negative 2 meters. Okay? Kilo, 1 kilometer, is 10 to the third meters. That's 1,000 meters. So if you know those definitions, you can easily write conversion factors. So these are conversion factors that I won't be giving you on a test. I would expect you to know what these conversion factors are because I'd expect you to know what these prefixes mean. Okay, milli, that's 1/1,000. It's 0.001, 10 to the negative third. So 1 milligram would be 10 to the negative 3 grams, or 0.001 gram. By the way, how many sig figs are in this 0.001 gram in this definition? Infinite, because that's an exact number. This number 1 right here also has an infinite number of significant digits. Okay, micro, that's represented by the Greek letter mu, lowercase mu, that's 10 to the negative 6. So that's 1/1,000,000th, 1 part in a million. Nano, we talked about this earlier, is 1 part in a billion, 10 to the negative 9. Pico is 10 to the negative 12. Okay? So those are some prefixes that you need to memorize. Those are the most important ones. A few units that you should be familiar with, particularly in chemistry, that are not necessarily SI but are still quite used a lot, is the liter. Okay? And that's defined as 0.001 cubic meter, or 10 to the negative 3 cubic meter is 1 liter. That's a unit of volume. If you imagine you have a cube, okay, the volume, and each side is 10 centimeters. What's the volume of a cube? Volume, length times width times height. 10 times 10 times 10 times 10, that's 1 liter. Okay? So 1 centimeter cube is called a milliliter. So if you have a cube that's 1 centimeter on each side, 1 cubic centimeter is a milliliter. If you have 1,000 of these milliliters, remember 1 milliliter is 10 to the negative 3 liters. Okay? Milli means 10 to the negative third. So if you have 1 liter, that means if you have 1 liter, you're going to have 1,000 milliliters. Okay, so that's a milliliter is 1/1,000 of a liter. So it's more popularly referred to in the medical field as a cc, cubic centimeters. So if you imagine a cube that's 1 centimeter on each side, that's 1 milliliter. If it's 10 centimeters on each side, then that's going to be 1,000 times bigger. That's a liter. Okay. Now, a liter is often expressed also as a decimeter cube because 10 centimeters is 1 decimeter. That's a tenth of a meter. Okay. A meter is 100. So 1/10 of 100 centimeters is 1 decimeter. So a decimeter cube is another unit that you might encounter for liter. Okay, so that's 1 decimeter cube. That's 1 liter. Now, a teaspoon has been officially defined by the U.S. government according to the United States Code of Federal Regulations, Section 101.9b5, Section 8. That is now defined to be exactly 5 milliliters. So that for something to be legally called 1 teaspoon, it has to be 5 milliliters. And of course, a tablespoon is 3 teaspoons, so that's 15 mils. If you have those measuring cups for your medicine bottles, you can take a look at those. You'll notice that you look at the labels. It shows milliliters on one side and teaspoons on the other. You'll notice that 1 teaspoon corresponds to 5 milliliters. All right. Now, let's relate that to some units that you're more familiar with. That's still used in the United States, still the legal system. It's called the English system of units. Okay, and so the unit that you know as the pound, as a unit of mass, has been officially defined as of 1959 by agreement between the United States and the Commonwealth of Nations to be 0.45359,237 kilograms. Or you can say that's about 454 grams. Okay, so you can run. This is the exact number. So if I say 1 pound equals 454 grams, how many sig figs do I have in 454? It's just 3 because I rounded it off. Okay, but if I say it's 0.45359,237, that's actually infinite because after the 7, it's all zeros. That's an exact number by definition. Okay, an inch is now defined to be exactly 2.54 centimeters or 25.4 millimeters. Okay, so about 25 millimeter is approximately an inch. So that's a good thing to remember, especially when you go to the lab and let's say the experiment calls for a test tube that is a common test tube you might find in the lab. Would be in the experiment might say find a test tube that is 25 by 150 millimeter. Okay, your test tube would be, let's say you are told find a test tube that is 25 by 150. What that means is the first number right there, that's 25 millimeters. You're looking at a test tube whose diameter is about an inch. So that's a 25 millimeter diameter. And 150, okay, 25 times 6 is 150. So that's about 6, I'm sorry, 20, yeah, so 150 millimeters. That's about 6 inches approximately. So you look for a test tube that is about 6 inches tall and it's about 1 inch wide. If you're looking for a 25 by 150 test tube. Question? Okay. Seems better at the moment. Okay, you got some lag? All right. Okay, all right. Did you miss anything I said? Okay. All right. Okay. So anyway, I just wanted you to be familiarized with the relationship between units that you're more familiar with, like inches and pounds, to the SI unit. So a pound is about 454 grams. That's about half a kilogram. So if you have like a French recipe for something, it will instead of saying use a pound of chicken, it might say use half a kilo of chicken, half a kilogram, because 500 grams, 454 is about 500 grams. So you can say, in fact, the more familiar equivalents you've probably seen elsewhere is like 1 kilogram is about 2.2 pounds, right? But the exact definition of the pound is it's 0.45359,237 kilograms. And an inch is 2.54 centimeters, or 25.4 millimeters exactly. Okay, so that's about okay. All right. So since there are many units that are in use, we need to be able to convert measurements expressed in one unit into another. And conversion is still fairly simple if you realize that it's really, when you attach a number to a unit, all you're really doing is algebra. So you can use what's called the method of algebraic substitution, or you can use the more familiar method known as the factor label method, and I'll show you later why that method works. Okay, and the idea behind the factor label method, dimensional analysis, is all you have to do is multiply whatever measurement you have to start with, multiplied by what's called a conversion factor. A conversion factor is just a ratio of equivalent values. Okay, and the thing you do need to remember when you're doing unit conversions, numbers that are relating units are generally exact. Okay, so when you're rounding off, if you do need to round off those numbers in the conversion factors, make sure that they're still more precise than the measurement that you are going to convert. So let's look at a couple of examples. Let's say you wanted to convert 3.5 millimeters to meters. Okay, here's a method you can use using algebraic substitution. All you have to do is this: 3.5 millimeters. What does milli mean? Milli means 10 to the negative third, right? So you can just say that's 3.5 times 10 to the negative third meters. And this is what you have right here. So that's equal to 3.5 times 10 to the negative third meter. Quick conversion right there. So that's a nice thing about SI units, those prefixes. You just replace them by the power of 10. And that allows you to convert whatever prefixed unit you have into the base unit, into the unprefixed unit. So now the factor label method, okay, what you do there is you write the measurement that you need to convert, and then you multiply it by a conversion factor. This is a ratio of equivalent amounts. You know that 1 millimeter is 10 to the negative 3 meters. Okay, so you put one of these in the numerator and the other one in the denominator so that the unit that you don't want cancels out. So millimeters is in the denominator here because that will cancel out the millimeters on the other side. Okay, so it's really just simple algebra. This is when you say it's 3.5 millimeter times 10 to the negative 3 meters over millimeter. It's really like saying like 3.5x, let's say 3.5y times 10 to the negative third x over y. Your y cancels out. So it's all multiplication. Anytime you attach a number to a unit, it's multiplication that's involved there. Right? So this is the factor label method. You start with the measurement that you know, multiply by a ratio of equivalent amounts so that the unit that you don't want cancels out. Let's look at a few examples. Let's say you want to convert 9.8 times 10 to the fourth meters to millimeters. Let's do this using algebraic substitution. You can just say it's 9.8 times 10 to the fourth. And what's a millimeter? 10 to the negative third meters. And so you're done. This is 9.8 times 10 to the 1 meters. Note that the number of sig figs before is 2 sig figs. You still have 2 sig figs at the end. Okay? So that's one way you can do it. That's another way you can do it. You can use conversion factor. So 9.8 times 10 to the fourth millimeter. Okay, so the unit that I want to get rid of is millimeters. So I put it down here so I can cancel it when I multiply. So this is my conversion factor. And the unit that I want to replace it with, I put on top. Okay, so I put meters up here. And I just need to know how meters and millimeters are related. So I know that 1 millimeter is equal to 10 to the negative 3 meters. So I can put 1 millimeter is equivalent to 10 to the negative 3 meters. There. And I should get the same answer. All right. Or if you prefer, if you're more comfortable, you already know that a meter is 1,000 millimeters. You can also do that. So you can say 1 meter is 1,000 millimeters. You get the same answer, which is going to be 98. Okay. Let's try this one. Convert nanometer to micrometers. Well, if you're going to look up the relationship between nanometers and micrometers, you might have a hard time finding it somewhere in the table. So, a good strategy is to change these first to meters and then change your meters to micrometers. And so let's do that using algebraic substitution. You can say 658 nanometers equals 658. What's a nanometer? Nano means 10 to the negative 9. So this is 10 to the negative 9 meters. Okay, so that gives me 658 times 10 to the negative 9 meters. So now how do I go from meters to micrometers? Well, let's see. I know that 1 micrometer equals 10 to the negative 6 meters, right? So if I divide both sides by 10 to the negative 6, I can say then that 1 meter is equivalent to 1 micrometer divided by 10 to the negative 6, or you can say that's 10 to the 6 micrometer. So remember, 1 over 10 to the x is the same thing as 10 to the negative x, right? So you can say then that this is equal to 658 times 10 to the negative 9, and instead of meters, we write 1 micrometer over 10 to the, let me put some room here. Let me redo that here. 658 times 10 to the negative 9 meters is equivalent to 658 times 10 to the negative 9. And a meter is this much, or 10 to the 6 micrometers. So 10 to the 6 micrometer. Think of it this way. Micro is 10 to the negative 6. Okay, so 10 to the 6 times 10 to the negative 6. These two together is just 1. Okay, so that's 1 meter. So the answer here then would be 658 times 10 to the negative 3 micrometer. Or if you want to do it properly, you want to express this as a number between 1 and 10, you move your decimal point 2 places to the left. So 6.58 times 10 to the, what would you have to do with your exponent? Left up, right? So from negative 3, you go up to negative 2 and negative 1. Okay, so 6.58 times 10 to the negative 1 meter. So that's how you do it using algebraic substitution. Let's summarize what I just did. What I did was I have 658 times 10, what was it? To the next, okay. I have 658 nanometers equals 658 times 10 to the negative 9 meters. That's equivalent to 658 times 10 to the negative 9, and a meter is 10 to the 6 micrometer. So that gives me 658 times 10 to the negative 3 micrometer. And so that's going to be 6.58 times 10 to the -1 micrometer. So that's how it's done using algebraic substitution. Now, if you want to do it using factor label or conversion factors, here's how you do it. You say 658 nanometers times, okay, I want to cancel nanometers, so I want to put nanometers down here, so it will cancel out. And I want to change it to meters first, okay? And then I convert it again to go from meters. I want to cancel meters this time, and I want my final answer to be in micrometers. So I do 2 conversion factors. So what's the relationship between a nanometer and a meter? Nano means 10 to the -9. So a nanometer is 10 to the -9, so that goes here. I'm going to say 1 nanometer is 10 to the -9 meters. And I know that a micrometer is 10 to the -6 meters. So that goes up there. I'm going to say 1 micrometer is 10 to the -6 meters. So I end up with basically the same answer. So all of this becomes 658 times 10 to the -9 divided by 10 to the -6, which is the same thing, 658 times 10 to the -3 micrometers. So that's 658 times 10 to the -3 micrometers. That's the unit that's left, which is the same thing as 6.58 times 10 to the -1 micrometer. Okay? Or you can write it as 0.658 micrometers. Any questions at this time? Okay. All right. Well, if you're comfortable with conversion factors, then that's fine. I'm not going to insist that you do the conversion a certain way. I just want you to be aware of another way of doing it, because sometimes the algebraic way is more convenient, and sometimes conversion factor is more convenient. I tend to flip-flop between the two depending on the situation. If you're plugging in a lot of numbers in a formula, for example, you'll find that it's a lot more convenient to use the algebraic substitution. Let's illustrate that with something like this. Okay, this is something you'll encounter when you do gas laws. Okay, the expression R, the constant known as the ideal gas constant R is 0.08206 liter atmosphere per mole per Kelvin. Okay, a liter is 1/1000 of a cubic meter. Okay, so in other words, if you had, imagine you have a box that's 1 meter on each side, 1 cubic meter. Okay, you're gonna have 1,000 liters in there. So if you buy 2-liter Cokes from Walmart, you're gonna need 500 of those 2-liter bottles to fill a box that is 1 cubic meter. So 1 liter is 1/1000 of a cubic meter, and a unit called the atmosphere, we use that for pressure measurements, is defined to be 1.01325 times 10 to the 5th Pascal. Okay, so how are we going to convert this from liter atmosphere per mole per Kelvin to cubic meter Pascal per mole per Kelvin? So what are we doing here? We're replacing meters by cubic meters, and we're going to replace atmosphere by Pascal. So here's how you can do it. You can say 0.08206 liter. So instead of liter, what am I going to write? 10 to the -3rd cubic meters. And instead of atmosphere, I'm going to write 1.01325 times 10 to the 5th Pascal. And per mole, oops, I me complete that here. Per mole per Kelvin. I'm not changing per mole and per Kelvin. So I'm just changing my liter and my atmosphere. Okay? So if you did this, what number would you get? Let's see. 0.08206 times 1.01325, that's 0.08314, times 10 to the negative third and 10 to the fifth. That comes out to, the whole thing comes out to 8.314 cubic meter Pascal per mole per Kelvin. Okay, so that's the value of R using the SI units. Pascal is an SI unit for a quantity called pressure. Cubic meter Pascal is actually a unit of energy. This is a joule. So you may see this later in our lessons, given as 8.314 joules per mole per Kelvin. So that's one way of converting that. Another way is, again, using conversion factors. So you can say R is 0.08206 liter times atmosphere per mole. Instead of writing per mole, you can write mole in the denominator. Okay, per Kelvin. Okay, so this per mole and per Kelvin right here, that means that unit is in the denominator. So I can do this way. I can do it this way. I convert liters to cubic meters, and then I convert atmospheres to Pascal. So I know that 1 liter is 10 to the negative third cubic meters, and I know that 1 atmosphere is 1.01325 times 10 to the fifth Pascal. So here, liter cancels out, atmosphere cancels out. So that's another way you do it, and you should get the same answer. 8.314 times 10 to joule per mole per Kelvin, or 8.314 cubic meter Pascal per mole per Kelvin. Okay. What about something like this? 1500 times 10 to the third square feet converted to square inches. Okay, 1 foot is 12 inches. How do we do this conversion? 1.500 times 10 to the third cubic feet. Square feet. Okay, so all I have to do is replace feet by inches. I'm going to say 1.50 times 10 to the third. Instead of writing foot, I would say 12 inches. And then square it. So this gives me, there should be an extra 0 there, 1.500 times 10 to the third times, what's 12 squared? That's 144 inches squared. Okay? So you can say, what is that number? 1.500 times 144, that's 216. Okay, so that's 216 times 10 to the third square inches. Okay, 1, 2, so that's 2.16 times 10 to the fifth square inches. Now, how many sig figs should I have in my answer? If you look at the original number has how many sig figs? 4, so my answer should have 4. So this should be written as 2.160 times 10 to the fifth square inches. Yes, the number 12 here, by definition, is exact. That's an infinite number of sig figs. 10 to the third, that's a power of 10. You don't worry about that. So the only thing here in your multiplication that has sig figs would be the 1.500. So that's 4 sig figs. So your answer should have 4 sig figs. Okay? Let's try that using conversion factors. You can say 1.500 times 10 to the third. So 1.500 times 10 to the third square feet. Square feet simply means feet times feet, right? So you need to do your conversion factor twice. So you can say, I want to change feet to inches. So 1 foot is 12 inches. That just gets rid of one of the feet. So I have to do my conversion factor twice, times 12 inches again. Over 1 foot. So your feet, another foot cancels out. So you end up with basically the same answer. You have 1.500 times 10 to the third, the original number, times 12 inches squared, which is really what we did earlier. See? The two are equivalent. Okay, 12 inches times 12 inches. So you should get the same answer that way. Or if you want to shorten this, you can just say 1.500 times 10 to the third square feet times, you can say 12 inches is equivalent to 1 foot, but you have to do it twice, so you have to square it. And again, common mistake people make is to forget about squaring this 12. This 12 has to be squared. So 1 square feet is actually 144 square inches. All right, so that's how you do it. How about this one? You have 2.5 grams per millimeter. I want to convert it to grams per meter. So I'm replacing millimeters by meters. Let's do the usual conversion factor method for this. I want to replace millimeters. So in my conversion factor, where does the millimeter go? Numerator or denominator? On top, right? That will allow me to cancel that. So meters goes down here. So what numbers go here? What number goes at the bottom and what number goes at the top? One meter is so 1 meter is 1,000 millimeters. So I can put 1 meter here, 1,000 millimeters up here. And that will give me my answer in grams per meter. Now, I could also say 2.5 grams per millimeter times, okay, again, I want millimeter on top and meter at the bottom, so I can cancel my millimeter. I can just go with the definition of what milli is. Milli means 10 to the negative third, right? So I know that 1 millimeter is 10 to the negative third meters. So 1 millimeter is 10 to the negative third meters. Either way, these two will give you the same answer. Okay? You get the same answer either way. All right. Here, given that an inch is exactly 2.54 centimeters and 12 inches is exactly a foot, how do you convert 7 centimeters to feet? We can do, let's do our conversion factor, 7.0 centimeters times. Okay, so if you look at your equivalents, I know I can go from centimeters to inch, right? Or vice versa. And 12 inches and foot in 1 foot, so I know I can convert from feet to inches or inches to feet. I have information given to me there. Okay. But the question is, if you're given the length in centimeters, how do you change it to feet? So you're going to have to do a two-step conversion here. What's the first step? Change it first to inches. So what unit goes on top here and what unit goes at the bottom? I want to cancel centimeters, right? And my centimeters is at the top right now. So centimeter goes at the bottom and inch goes on top. So what's the relationship between inches and centimeters? 1 inch is 2.54 centimeters. So 1 inch is 2.54 centimeters. That allows me to get rid of centimeters. Now I want to get rid of inches. So in my next conversion factor, where does inch go? The bottom, and feet goes on top. That allows me to cancel inch. So what number goes with inches down here? Relationship between inches and feet. 1 foot is 12 inches. So 1 foot is 12 inches. And so what does this give us? Someone get it from the figure it out on a calculator, please. What is it? What is it? Can someone type it in the chat box? Okay, so it's 0.229658, and so on. 7927. How many sig figs should I keep in my answer? Two sig figs. So the first non-zero digit, that's where you start counting. 1, 2. Why only 2? Because this has two sig figs. All right. 2.54 has how many sig figs? Not 3. Infinite. The 12 here has how many sig figs? Infinite. The 1 has infinite. This one has infinite. So 7.0 is the least precise term in this calculation. 2 sig figs in your original measurement. In your converted measurement, also keep 2 sig figs. So this should be rounded off to not 0.22, but since the number you're dropping is a 9, 0.23 feet. Okay? All right. Why do these methods work for unit conversion? The reason for that is that the quantities that are expressed in these units are what we would call directly proportional. This is a very important mathematical concept that we use a lot in chemistry, so this would be a good time for us to go over this idea of direct proportionality. You say two things are directly proportional, okay? Let's say x and y are two things that are directly proportional. When we say they are directly proportional, it means that if x is 0, y must also be 0. And, so that's one condition. And the other condition is that x divided by y must always be a constant, must give you the same number each time. Okay, so the ratio is constant. So this is in fact the definition of direct proportionality. Two quantities are directly proportional if x over y is a constant. So if x, what this means is if x changes, then y will also change by the same factor. What that means is if I double the amount of x, it automatically means that the amount of y also doubles. If I triple the amount of x, the amount of y also tripled. If I cut the amount of x to half, then the value of y will also be cut in half. Okay? Let's look at this example right here. Length in meters, we say, and length in centimeters are directly proportional. Well, let's see. If I have 1 meter, what's the equivalent amount in centimeters? 100 centimeters. If I have 2 meters, if I were to double it, what's the equivalent amount in centimeters? 200, twice as much. See, that's how you can, that's a quick way to tell if two things are directly proportional. Try to double one. If the other one would automatically double, if we double the other, then that means they are directly proportional. Well, let's get the ratio of these two things. So let's call meter, the amount length in x, meter is y, x, and the length in centimeters as y. Let's take the ratio of x over y. What is x over y? In this particular instance, what's x over y? 1 meter over 100 centimeters. Is that equal to the ratio in this particular instance? 2 meters over 200 centimeters. Is 1 over 100 equivalent to 2 over 200? You know, you can, this is a fraction, you can reduce this, divide both numerator and denominator by 2, you get 1 over 100, right? So the ratio of two things are, in this particular case, the ratio of the length in meters to the length in centimeters is a constant. That's what we mean by direct proportion, directly proportional quantities. Okay? That helps you a lot in solving a lot of problems in chemistry, because a lot of the things we deal with in chemistry are directly proportional. All right, so let me rewrite this. I can say the length in meters, in other words, in meters, divided by length in centimeters equals 1 meter over 100 centimeters. All right. So what if I knew my length in centimeters to be, what if this was, let's say this was 5 centimeters. Okay, then I'm going to have to say x over 5.0 centimeters equals 1 meter over 100 centimeter. I'm just substituting. Let's say I wanted to know what the length in meter is. I call that x. Right? X over 5 equals 1 over 100. So how do I solve for x? You multiply both sides by 5.0 centimeters, right? The way you do it in algebra. So you say, multiply both sides by 5.0 centimeters. That will get rid of the 5.0 centimeters here. So I'm going to say, then basically you move that over there, right? So x is equal to 5.0 centimeters times 1 meter over 100 centimeters, which is exactly what we've been doing when we were doing conversion factors. The unit that you have, the measurement that you know, you just multiply it by a ratio of equivalent amounts, your conversion factor. And that works because that method for conversion works because your quantities are what we would call directly proportional quantities. Okay? So this is a math skill that you need to be able to be very comfortable doing if you have proportional quantities to solve for an unknown. All right. What about temperature conversions? Well, temperature readings, okay, in Celsius, Fahrenheit, and the Kelvin scale are not directly proportional. Okay, so And a quick way to tell is that 0 on the Celsius scale does not correspond to 0 on the Fahrenheit scale. A reading of 0 on the Celsius scale is 32 degrees on the Fahrenheit scale. It's 273.15 on the Kelvin scale. So you cannot use conversion factors when doing temperature conversions. What you can do is you can just use the defining equations that relate these quantities. So the defining equation is, in the case of Celsius, okay, whatever temperature you have in Celsius, you multiply it by 1.8, okay, and then add 32. Now, for unit consistency, since this is going to be degrees Celsius, the 1.8 unit must be degrees Fahrenheit over degrees Celsius. That way, your unit cancels out. And so you can add, this result of this multiplication should be in Fahrenheit. So you add that to 32 degrees Fahrenheit to get the temperature in Fahrenheit. Same thing here, to convert from Celsius to Kelvin, whatever temperature you have in Celsius, okay, then you have to multiply it by 1 Kelvin per degree Celsius. That way your degree Celsius would cancel out before you add the 273.15. So this 1 right here is usually not mentioned. You just told add 273 to get to the Kelvin scale. That's basically what you're doing. But if you want to do it properly with all the units correctly indicated in your calculation, whatever temperature you have in Celsius, you have to multiply it by 1 Kelvin over 1 degree Celsius. Okay, so that's just the formal way of doing it. All right. Now, so let's do some calculations here. 25 degrees Celsius, typical laboratory temperature. What would that be on the Fahrenheit scale? So you plug in the numbers. 1.8 degrees Fahrenheit over 1 degree Celsius. So these numbers, 1.8 and 1, are exact, multiplied by the temperature in Celsius, which is 25.000 degrees. Degrees Celsius cancels out, so you can see now this multiplication gives you degrees Fahrenheit, and then you add 32 degrees Fahrenheit, and that 32 is exact. And so that number comes out to 1.8 times 25, that's 45. How many sig figs should I keep here? 5. Okay, 25.000 has 5 sig figs, 1.8 has infinite, 1 has infinite, so this is 45.000, and then I add 32. Okay, and so this will give me my answer in Fahrenheit. What is 45 plus 32? That's going to be 77. How should I report this 77? Plain 77 or 77.0, 77.00, or what? 45.000 plus 32. How should I do this? Okay, I know that 32 is exact, so that's the same thing as 32.000000000. So if I add these two, my answer should be 77.000 degrees Fahrenheit. Okay, let's try Kelvin. We need to convert 25 degrees Celsius to Kelvin. So temperature in Kelvin is equal to 1 Kelvin per degree Celsius times the temperature in Celsius, add 273.15 Kelvin. Okay, so now what do I do? That's equal to whatever Celsius reading I have, 25.000, 3 zeros, right? 25. So 1 Kelvin over 1 degree Celsius times 25.000 degrees Celsius. plus 273.15 Kelvin. So if we did this first step right here, 1 times 25 is 25. How many sig figs do I have here? Celsius cancels out. 5 sig figs. So 25.000 plus 273.15. And that gives me, so 25.000, 273.15. That's 298.15. Is that enough? Or should I add an extra 0? 273.15 is an exact number, so there's extra zeros there implied. Okay, so my last sig fig would be that. So this is 298.150 Kelvin. I forgot to put Kelvin here. You're adding, so the rule for addition is you go by the decimal place of the last sig fig in the least precise term. All right, so that's how you do conversions from one temperature scale to another. Now, the thing to realize, though, is if you're looking at temperature changes, okay, or differences in temperature readings, those are actually directly proportional. So a change in the Kelvin scale compared to a change on the Celsius scale would be 1:1. That is, in fact, that number that you put in front of the temperature in Celsius, this thing right here. This is actually delta T in Kelvin divided by delta T in Celsius. That ratio is a constant. Okay, so changes on the Celsius scale and changes on the Kelvin scale are directly proportional. Let's illustrate that. For example, okay, let's just quickly illustrate that. A 0 degree Celsius, what is it on the Kelvin scale? 273.15, right? This is degrees Celsius. If I were to do 5 degrees Celsius, what would that be on the Kelvin scale? How do you go from Celsius to Kelvin? You just add 273. So 5 plus 273 is 278.15. Okay? A change of 5, if delta T on the Celsius scale is 5, delta T, anytime you use the word delta before a symbol, that means change in whatever that symbol is. So delta T means change in T, right? Or difference in the T values. So a delta T of 5 corresponds to what delta T on the Kelvin scale? 5 degrees Celsius corresponds to a change of 5 Kelvin. All right? What if I did a delta T of 10? Delta T Celsius is 10. What's delta T on the Kelvin scale? What would this be on the Kelvin scale? 10 degrees Celsius on the Kelvin scale is 283. Okay, whatever Celsius reading you have, you add 273.15, you get your Kelvin reading. So what's delta T on the Kelvin scale? 283 minus 273 is 10, right? So can you see that delta T Celsius, Kelvin over delta T Celsius, it's 5 over 5. 5 Kelvin over 5 degrees Celsius is equivalent to 10 Kelvin over 10 degrees Celsius. Okay? That ratio, 5 over 5 is equal to 10 over 10. That's equal to 1. So this is 1 Kelvin per degree Celsius. By the way, Kelvin should never be written with a degree symbol. Kelvin is what we call an absolute temperature scale. So there's no degree symbol written when you write temperatures in Kelvin. Okay? So Changes on the temperature scales are directly proportional. Same thing with Fahrenheit and Celsius, okay? And that's where that 1.8 in the formula comes from. Every time your Celsius reading changes by 5, your Fahrenheit reading changes by 9. 9 over 5 is the same thing as 1.8 over 1. Okay? You do your plug it into your if you plug that into your calculator, you can say that 9 divided by 5 is 1.8. That's where that 1.8 comes from in the formula. By definition, okay, that means as agreed upon, as defined, a change of 5 on the Celsius scale corresponds to a change of 9 on the Fahrenheit scale. So those changes or differences in temperature are directly proportional. So let's apply that to this question. Temperature goes up from 25 degrees to 34 degrees Celsius. What's the change in the Celsius scale? The final value, 34 degrees Celsius minus 25 degrees Celsius, that is 9 degrees Celsius. By how much did the temperature change on the Kelvin scale? What's the answer? Also 9. You can say 9 degrees Celsius times 1 Kelvin over 1 degree Celsius. Okay, so degrees Celsius cancels out. That gives you a change of 9 Kelvin. Here's the long way of doing this. You can just say delta T Kelvin would be, okay, 34 plus 273 minus 25 plus 273. Okay, so this is the final temperature in Kelvin. You add whatever Celsius you have, you add 273 to it. And then whatever Celsius reading you have before, you add 270 to that. You can see that if you did this, what happens to 273? It just cancels out. So that's just 34 minus 25. That's just 9 Kelvin. Okay? All right. Temperature changes from 50 degrees Celsius to 62 degrees Fahrenheit. By how much did the temperature change in degrees Celsius? Well, what's the relationship? Delta T Celsius to delta T Fahrenheit is, let's do Fahrenheit to Celsius. Delta T Fahrenheit to Celsius, that's 1.8 is to 1, right? 9 is to 5. That's where the 1.8 comes from. So, but how much did it change in degrees Celsius? What's our delta T in Fahrenheit? Change in temperature. The final temperature is 62.0 degrees Fahrenheit minus 50 degrees Fahrenheit. You're looking at a change of... Question? Oh, okay. What's the answer? I can barely hear you. 21.6? All right. Now let's see. All right, so you have 12.0 degrees Fahrenheit. The change in Celsius then would be 12.0 degrees Fahrenheit times 1 degree Celsius corresponds to 1.8 degrees Fahrenheit. Okay, note that this conversion factor here, okay, you can flip it. If you flip it, it's going to be 1 over 1.8. So here your Fahrenheit cancels out. It's not 21.6. 12 divided by 1.8, that gives you 6.67. So this is 6.67 degrees Celsius. Okay? Let's see if this makes sense. The Fahrenheit change should be larger than the Celsius scale. Remember on our scale, every time your Celsius changes by 5, okay, on the Fahrenheit scale, the change is 9. 9 is to 5. So the Fahrenheit change must be bigger than the Celsius change. Right. Now, if you want to do this the long way, here's what you would do. Okay, delta T Fahrenheit. Okay, what's the final reading in Fahrenheit? What was our Celsius reading? 62. So 62 times 1.8 plus 32. Okay, that's your final Celsius. Oh, it's Fahrenheit. So how do I go from Fahrenheit to Celsius? So if Fahrenheit is Celsius times 9 times 1.8 plus 32. How do I solve for Celsius if I know Fahrenheit? I need the change in Celsius, right? I subtract 32, right? And then divide by 1.8, correct? Let me do that here first. I say the Celsius reading is whatever the Fahrenheit reading is, I subtract 32, and then I divide by 1.8. Okay? Let's do that step by step with algebra. Okay. Subtract 32 from both sides. That gets rid of the 32. And then divide both sides by 1.8. That gets rid of the 1.8. So whatever Fahrenheit reading you have, you subtract 32 and you divide by 1.8, you get your Celsius reading. So now let's calculate our change in Fahrenheit reading. Delta T on the Fahrenheit scale would be, change in the Celsius reading. Delta T on the Celsius scale would be, what's our final Fahrenheit temperature? 62. Okay, so you're going to say 62 minus 32 divided by 1.8. And then the initial Celsius reading is 50, right? So you went from 50 to 62. By the way, this is 62.0. And the initial one is 50.0. That's your Fahrenheit reading. You subtract 32, you divide by 1.8. Okay? Now you can calculate this individually and then you get the difference and you should arrive at the same answer. Or you can manipulate this algebraically, you can simplify it. How do you simplify it? You have the same denominator, so you can put everything over 1.8, right? So this is going to be 62.0 minus 32 minus 50.0 minus 32. You'll notice the 32 doesn't factor into your calculation at all. What is 62 minus 50? That's just the change in the Fahrenheit reading. Essentially, you're just dividing it by 1.8. So you're multiplying by 1 and dividing by 1.8. Whatever the change on your Fahrenheit scale is, you're essentially dividing it by 1.8 to get the change on the Celsius scale. So what you have here would just be 12.0 over 1.8. And that would be the change in degrees Celsius. So that's going to give you 6.67 degrees Celsius. Okay? So that's a change in temperature. A comment about temperature changes. This is in some old textbooks, instead of saying degrees Celsius, they say Celsius degrees. Okay, and some textbooks are still using that. I believe if you're in your physics class, I think Mr. Chauvin still uses Celsius degrees. Okay, so that's a good way to make a distinction between change in temperature and an actual temperature reading. But the modern convention these days in most textbooks, they don't make a distinction between these two anymore. Okay, so you just have to know from context, are you dealing with an actual temperature reading or are you dealing with a temperature change? Because it makes a difference when you do your conversions, whether you're going to have to add the 32 or subtract the 32 or not. Okay, and the same thing with Celsius and Kelvin. Right. So temperature changes. If you're taking physics, you might see that written as Celsius degrees instead of degrees Celsius in some classes. Any questions at this time? Okay. All right, so here's a clicker question. Oh, okay. So they're familiar with it. So temperature of a mixture dropped by 10.0 degrees Celsius. By how much did it drop in Kelvin? Okay, temperature dropped by 10 degrees Celsius, so the Kelvin would also drop, right? And so the answer is, for every degree Celsius you drop, you're going to drop 1 Kelvin, so the correct answer is A. Okay? So when you say it dropped, you're looking at a change of 10 degrees, or 10 Kelvin in this particular case. All right. Now, I've mentioned that units generally come with measurements. When you have a measurement, you have a number and a unit. Okay. There are some things that you measure that you don't attach units to, and when you report those, okay, so it's not true that all measurements must have units attached to them. Some of these quantities that are unitless, when you report them, it has to do with the fact that based on the definition of the quantity, it should come out unitless. So, for example, okay, a quantity called specific gravity. By definition, it's the ratio of the density of the sample to the density of a reference material. So that's density of a sample divided by the density of a reference material, and usually in the case of liquids, the density of the material is water, the reference material. So what would be the unit for specific gravity? Well, it would be the unit for density. What's density? Density is mass over volume. So it's grams per milliliter, for example. So your unit for the numerator is grams per milliliter. Your unit for the denominator is also grams per milliliter. So specific gravity is unitless. Okay. Transmittance is another quantity we encounter in chemistry that's unitless. It's the ratio of the intensity of light, okay, that's passing through a sample. So if you have a sample, a liquid, and you pass light through it, the intensity of the light that passes through it, so here's my light bulb right here. You measure the intensity that passes through it. Divide that by the intensity that passes through a reference sample. So I over I reference, that's called your transmittance. So whatever the unit for intensity is, that's the unit in the numerator, and the denominator, those units cancel out. So transmittance is also a unitless quantity. Anytime you take the log of something, usually you take the log of something that's unitless. So the logarithm quantities that are calculated using logarithms are also unitless. So absorbance is an example. It's by definition, the absorbance of a solution is the negative of the logarithm of the transmittance. So transmittance is unitless. You take the logarithm of a unitless quantity. Absorbance is also unitless. Okay, so question? Sure, I'll put it on Moodle. Yeah, I'll have it set up for a time window during your class time. Yes. Um, when they come back, we can turn on that quiz during the time that they're doing a makeup test, just for that. Yeah, we can turn that, we can turn the quiz on and off at any time. So if they need to take a makeup, we can do that when they come back, or they can do it earlier if they want to. But I have to set it up sooner. No, I won't be able to set it up in time. Okay. All right. So there's a few more clicker questions. I think you'll see a bunch of these on the homework anyway. So these are just things for you to think about, to practice on. If you want the answers to these, uh, there's a series of videos actually answering these questions that are posted on YouTube. I can give you the link, but if you'll probably see this in the homework, and the homework will give you the link to the YouTube videos. Okay. Yes. Uh-huh. Right. Mm-hmm. Okay. Yeah, I might try TeacherTube next time and see if I. You can get through TeacherTube on your site at your school, right? Yeah, I think Gaggle filters it, but I don't know if it passes through Gaggle's filter. I'm not sure if it will pass through your school's filter either. So okay, yeah, I'll have the quiz ready for Friday. All right, and yeah, I'll be around Friday too if you need me on the free Moodle site. Yes. All right, that's good. So this basically is a review of measurements. So they usually don't cover this in Chem 105 here anymore. So so next week we start Chem 105 officially. All right.